रेकॉर्डिंग चालू आहे ते पण चालू आहे.
स्टुडिओ मोड
पण ते काय गरज नाही स्टुडिओ मोडचं. स्टुडिओ मोड म्हणजे फुल स्क्रीन होईल का?
बघू का
नको ते
जाऊ
तसं हा इकडे येतं का मला? आपली चालू नाही झाली ना? यूट्यूबला तिथं इथं नाही येत ना चालू केल्यावर येतं.
दिसत का नाही इथं?
झालं का चालू?
नाही हे का दिसत नाही.
मल्टिपल करा ना ते त्याच्यात.
ऍडमिट नाही ही विंडो का नाही दिसत आहे?
इथं इथं
झाली.
घेतलं इथं स्टार्ट झालं
लाईव्ह
पण स्टार्ट नाही झालं
आपला इनबिल्ट पण रेकॉर्ड करतो.
हा लोगो कुठून आला?
तो कोणाचा आहे जो आहे त्याचा आहे.
पिन बिन करून आपलं पिन करा. लिंक पाठवू का?
हां
ते सर झाले का आले का प्रशांत सर? चालेल नाव दिसत नाही. त्याचं काय करायचं लोकांना?
एक मिनिट प्रशांत सर दिसतंय का बघू आता. त्यांचं नाव काय आहे?
प्रशांत
नाही आलेलं अजून.
ते सगळे काय ट्राय करायला आपल्याला त्यांना पहिले घ्यावं लागेल. शेवटी काय एखाद्याला पण आपण काय आपलं
आपला ऑडिओ पण रेकॉर्ड स्ट्रीमिंगला.
मग सरांनी काल काय केलं होतं सरांनी इथून हे केलं होतं ना साऊंड बंद केला होता ना नाही घेतलं रेकॉर्डिंग बंद करण्यासाठी.
हो पण तो नाही येणार ना तो.
जाऊन द्या याच्यावरून जातं किती झालं 20 22 23 खटी येत होते. शोधावं लागेल. युट्यूबचं झालं ना ती पण लिंक पाठव ना. मॅडम लिंक कुठून केली होती?
इकडून पाठवते माझ्याकडे.
तुमच्यातून पाठवते का?
आणि आपण जे बोलून असेल बाहेर ते पण रेकॉर्ड होतं.
त्याला बोलायलाच नाही पाहिजे. लिंक कुठून यूट्यूबची लिंक कुठे
आहे माझ्याकडे मेल.
इथून कशी घ्यायची इथून कशी घ्यायची कशातून घ्यायची
मी कॉपी केलं.
नाही हे नाही लिंक 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 कॉपी लिंक
लिंक
कसं
नाही घेतली, डायरेक्ट आपली स्क्रीन दाखवली. इथून
म्हणजे
स्टार्ट स्ट्रीमिंग केलं ना की डायरेक्ट ही स्क्रीन ओपन केली. ही दिसते. हे करा मिनिमाइज करा. रेकॉर्डिंग होतं आहे. ऑरेंज बॉर्डरमध्ये रेकॉर्डिंग होतं.
नाही नाही आता आपल्याला यूट्यूबची लिंक शेअर करायला केली ना आपण
हां
ती लाईव्हवाली
हां हां.
त्याची लिंक कसं काय करायची लिंक तुमच्याकडे कशी आली
इथून शेअर करायची.
अच्छा इथून करता आहे शेअर लिंक माझ्या ह्याच्यात तर प्रॉब्लेम आहे यूट्यूब तर घेतात नाही माझ्या सर्च कशी करू ते हां पहिले लॉग इन होतो सर्च कशी करू इथे सर्च करावं लागेल का डे टू कुठे डे टू वाली कुठे
नाही तुमच्या ह्याच्यावरून करा तुम्ही. तुमच्या ह्याच्यावरून येत पण नाही. तुमच्या ह्याच्यात दिसलं पाहिजे.
गेले 50चे पुढे ते सरांना फोन केला का यूट्यूबला चालू झालं ना यूट्यूबची लिंक पण शेअर करतो खूप फास्ट आहे बरं
मला दिसतंय तुम्हाला नाही
झाली
दिसत. मग
किती झाली 60 65 चांगलं आहे
नेटवर्कचा प्रॉब्लेम आहे.
मी लॉग इन नाही झालो बरं
तुमच्या ह्याच्यात फीड्स मोड ऑन झाला.
रिस्ट्रिक्शन ना
फीड्स मोड ऑन झाला आहे तुमच्या ह्याच्यात.
शेवटी असेल
मी आत्ता पाठवलं.
रिस्ट्रिक्शन मध्ये गेले पॅरेंट याच्यामध्ये
तुमचं
गेलेलं
पॅरेंट मोड ऑन झालं.
हॅलो बोल मी बोलते की मला एकच
कॉलचे
काय केलं हां बरं केलं
हे कॉलचे
कालचं आहे आलं वाटतं ना
तुमचा रेस्ट्रिक्टेड मोड ऑन आहे. दुसरं लागलं नाही का कोणतं.
दुसरं आहे ना FDP सपोर्ट
नाही
आपलाच आहे
हे चॅनल आहे आपलं.
चॅनल आहे फक्त लिंक पाठवायची काय येते नाही
हां
येतं ना यूट्यूबचं
एकदा करून बघा ना.
चार्जर बटन चालू करा. तुम्ही केलं ना? आजच्याच आहे बरं. कोणाला करायचं आहे का? मी केलं. नंतर आउट होईल. झालं आता. मी बाहेर पडलो.
Hello, Prashant.
Yes, sir. I'm here.
Shall we start?
Yeah, we can start.
Yes. Anushka Madam will brief about today's session and then you can continue.
Okay, okay.
Anushka Madam, proceed for.
Yes, sir. Good morning, everyone. Good morning, everyone, and greetings of the day, and warm welcome to all respected participants and Vice Principal Sir, and our resource person for today is Mr. Prashant Kadam Sir, and all the professors. I, Anushka, would like to welcome you all to the day 2 of 1 week faculty development program on harnessing intelligence deep dive into machine learning. On the behalf of SRTTC AIDS department. So let's embark on this incredible journey and learning and discover with that. Let's just begin our day 2 session. I would now like to hand over to Mr. Kadam sir to please proceed.
Hello, can you hear me?
Yes, sir.
Okay, all right. So I'll share my screen. Let me know once you're able to see the screen. All right, is it visible?
Yes, sir. Now it's visible.
All right. So good morning, everyone. Today we are going to continue from where we left yesterday. Yesterday, what we did was a brief introduction to machine learning. What are the different types of machine learning? What are the different applications of machine learning? And we also understood bias and variance. We also understood what optimization is and why is it important. And finally, we took a look at gradient descent, which is a very commonly used optimization technique. We also looked at stochastic gradient descent yesterday. And today, what we're going to do is we're going to start with supervised machine learning. So we're going to start with some very legacy algorithms, as they are called in machine learning literature. With there's some disturbance. Yeah. So
Hello, sir.
yeah, I can hear some disturbance. I think someone unmuted.
Yes, sir. Your screen is not visible. Can you share it?
Okay. How do we share the screen? Is it not visible? I can see it.
No, sir.
Oh, okay. Let me reshare. Is it visible now?
Yes, sir. It's visible.
Okay. All right. So, moving on. Today we are going to start with some basic machine learning algorithms like regression. Like we'll start with linear regression, and then we'll move on to logistic regression. These are the two topics that we are going to cover today. Uh, these are the most basic supervised machine learning algorithms that have a wide range of applications. Again, they are very basic algorithms, as in they are not able to fit to very complex applications. But yeah, eventually you will learn that even the most complex models like deep learning neural networks and these large language models, these are all essentially made up of these logics or logistic regression modules. So these essentially um, these will play a very big part as we move on with the course. So so to start with, let me give you a brief overview of supervised machine learning, what we learned yesterday. Was so basically, in case of supervised machine learning, you already have the data with you, right? So you have the input labels, and you also have the target label with you. You are going to train your model using the inputs as well as the target. For example, you you have a bunch of different features about a certain, let's say about a certain flower. You have the size of the petals, the number of petals, and then you can, and the target is the name of the flower. So you, using all this information, you can essentially predict the name of the flower. So in your initial data set, you will have all this information with you, and what you're trying to do is trying to predict that. And this type of learning is called supervised machine learning. You're trying to learn a function f of x that essentially can give you the value of the target variable. There are two types of problems, a regression problem and a classification problem. Regression is essentially you're trying to predict a value, a continuous value. So, for example, what is the age of a person, what is the weight of a person, or something like that. You're trying to predict a continuous value. And categorical is when you're trying to predict a specific category. Like when I gave you the example of a flower, when we're trying to predict a flower is a specific category and not a continuous value. So that comes under that is counted as a classification problem. And the other one where you're predicting a continuous value is considered as a regression problem. So moving on, linear models. So basically, you're just what essentially you're trying to do in these linear models are you're trying to predict a line through a best fit line through your data set, and that line will essentially help you to predict values for your unknown data of the target variable. So these techniques are considered old school, and they're often not as predictive as some of the newer, more complex algorithms. But they perform very well in certain scenarios, and they are extremely fast at the time of inference. So based on your use case, these techniques could be very efficient depending on where you apply these methods. So linear regression. So we'll cover two types of linear models. So one is a regression-based model where we are trying to predict the value, which is linear regression, and then logistic regression, where we're trying to predict the category. So it's a classification problem. So that's where we will use logistic regression. But both of them are just linear models that we'll be exploring today. So let's begin with linear regression. So just to give a visual of what a data set would look like. So we will just be considering univariate analysis. Basically, what that means is I have a single variable X, and using that variable, I'm trying to predict Y, right? So you can, in this particular plot that you see on your screen right now, you can see that the x-axis is the customer's age. So let's say a customer coming into a shop, how much would a customer spend based on their age? Now I know that this doesn't really make sense, but for the sake of this illustration, let's say this data is actually it actually makes sense. Like as the customer's age increases, the amount of money spent by the customer in that shop increases. So that's what you see. So if you see all these data points, you can see that as the age increases, the amount spent per week is increasing steadily, and there is a linear trend to the increase. So of course there is some variability. Not all the data points lie along that one red line that you see, but still, roughly the whole distribution is following a linear increase in the spend per week. So in these kind of distributions, a linear model would work very efficiently. So, and that's what we are trying to learn in this case. We are trying to learn how we can fit this one line through this data, so that if someone comes to me and says that, okay, I have a person who is maybe say 62 years old, what would be the amount that the person is spending? So I could easily go and substitute this value 62 in the equation of the line that I have learned from my linear regression, and I could come up with this value essentially, which is around 32 maybe. Yeah. So that's what we're trying to do. So this is what we're trying to do out of linear regression. So let's get started. So we are trying to fit a line through this whole data set. So what is a line? So line is essentially, it can be defined as y is equal to mx plus b, where m is your slope, b is the intercept, right? So these are the basics of a straight line, I guess. And x is your value, x is your feature that you have with you, and y is your target variable that you're trying to predict. So essentially, through this data set, you are trying to basically draw this straight line that can effectively represent your data. Moving on. So now, suppose, how do we start with this problem of this linear regression? How do we start with this linear regression problem? So let's say we start with this horizontal line, right? So I look at this distribution of data over here. So we have a plot in which there are a bunch of data points, and what we are trying to do is we are trying to draw a straight line through this data set. But we don't know where to start, right? Like we can't just draw a line like this and say that okay, this is the optimal line. We have to start somewhere and then eventually optimize and then reach the best fitting line through that data. In order to do that, let's say we start with a horizontal line randomly, and from this we will see how good this line is fitting the data, and through that we will start tweaking it. So now that I have this line with me, what I can do is I can see what is the error that the line is generating. Like, what is the error between each data point and the line, right? So for example, if you see this data point over here, so this is the difference in the value of the line will be predicting this value, but the actual value is this. So this is the error, or it is called residual, right? So this similarly we can calculate it for each of these data points, right? We can calculate them for each residuals for each of the data points, and then we can sum them up, right? To see that what is the net error that this line has. So what is the net value for that particular line. But now the problem is some of these values lie below the line, some of these values lie above the line, right? So if I'm taking the sum of all these values, what will happen is these values are going to be negative, these values are going to be positive, the upper values. So what would happen is they would essentially negate each other, and it could be possible that they would almost reach zero, which would mean that it is a perfectly good fit for the data. But obviously it is not, as we can see. So essentially we need to maximize using the magnitude of the data, magnitude of the residuals, and not just the actual values, right? So what we do is we square them. So each of these values, what we get here, we square them and then we sum them. So as you can see in the equation at the bottom, we are taking the squares of each of those data points, and then we are summing it up, and then we come up with a value, right, which we call as the least square value, and which we call the least square value, and then we further optimize on it. So now from here, what we understood is we drew a horizontal line through the data. We calculated the difference between the values of the values on the line and the actual values in the data set, right? And then we found the error between the line and the actual data, squared it, and summed it up. So now for this line, we got a net error, right? What we want to do now is maybe what we can do is now we can tilt the line slightly, right? We can rotate the line a little bit to see that is the sum of squared errors any better now. So that's what you can see in this diagram over here. We have tilted the line a little bit, and intuitively you can make out that okay, the sum of errors is definitely going to be, because the line is fitting the data much better, and the distances between each individual points and the line seems to have reduced now. The sum of squared errors in this case is going to be lesser than the first horizontal line. So this is a little better, right? And then we can tilt the line a little further maybe, and then so this way we keep tilting the line and we calculate the sum of squared errors for each line, for each different slope of the line. We keep on calculating that value, and then what we do is, let's say we plot that value, right? So as you can see here in this plot, for horizontal line, see this is the horizontal line, I got this as the sum of squared errors. For a little tilted line, I got this. For more tilted line, I got this. Then a little more tilted line I got. So as you can see, by the time I reach vertical line, the sum of squared errors is increased again, right? So what I want to do is essentially, I want to run an optimization on this curve that you can see here, right? And the point where I'm getting the minima of this curve, and as you can see, this is a convex curve, and from what we learned yesterday, we could run a gradient descent on this in order to get that value. So uh, basically, we are rotating the line continuously, and we get all the possible sum of squared errors, and then we want to reach the least squared value by minimizing over the sum of squared errors curve, right? And that is going to be the optimal value of the slope of that line, right? And that is going to be my m. So this gives you an intuitive understanding of how linear regression is working, right? That you start with a random line, you start twisting the line a little bit. Also, there is the concept of intercept. So as you can see, the line is not actually passing through the origin, right? So this line is not passing through the origin. So there is some value of C over here, which also needs to be considered and which also needs to be learned. So there are two parameters that we are trying to learn. One is the slope and one is the intercept. But essentially, this is the technique. This is a high-level overview of how the process of fitting data to a line looks like. Now, as you can see, we can, once we plot each data point, right? Once we plot the sum of squared errors for each different angles or each different slope of that line, we could get a curve like this, and then we could probably reach the minima of that curve to find the optimal value of that particular parameter that we are trying to optimize. Now, intuitively this makes sense that okay, we can do this, but practically, when you're trying to implement this technique, you can't really do infinite tilts of the line, right? You won't be calculating least square values. For some of the squared errors for all the possible slopes, which are like infinite number of slopes. So you can't really do that. But so in that case, what you know is that you are optimizing on the sum of squared errors, right? So you can essentially, so you know what the curve looks like. So you can run a gradient descent on that. Maybe I can actually show the process of gradient descent. So for example, by what I mean by when I say that you can run a gradient descent on that curve, what I mean is, so you essentially know that you're optimizing over the sum of squared errors, right? So let's say you have some weight, some bias that you're trying to optimize on, right? And you are essentially, you have some target value, which is your yi, and let's say this is the equation of your line, that is your predicted value, right? And what you're essentially trying to do is you're trying to optimize on this value. So this is your equation that you're trying, this is your cost function that you're trying to optimize on, right? So basically, if you can take, and you have two parameters that you're trying to optimize, right? So what you can do, and that is your slope and your intercept. So what you can do is simply take partial derivatives with respect to each of the parameters, right? So then you will get something, let's see, this would be xi and then the whole thing in. So which would be like this. Uh, yeah, that's correct. And again, when you take partial derivative of the same of this equation with respect to your intercept value, you will get something like this. So you are summing over all the data, and for intercept, yeah, so this will become y minus the same thing. Side basically. So this essentially will be your partial derivative with respect to your with your slope, and this is going to be with respect to your intercept, right? It's pretty straightforward. And then what you are doing is you are simply running gradient descent. So you are updating the values of your slope by taking the older slope and then you're taking the net step. So this again, this is your learning rate, uh, and then you're multiplying the learning rate and by the gradient. So this becomes your gradient, and this is how you update. So this is your update step, where you're essentially just updating the value based on the learning rate and the gradient that you calculate. This is how after running n iterations, you will come up with some optimal value where you will reach the minima of that convex curve that basically your least square curve which you're trying to predict, right? And then that becomes the value of your parameter, which could be slope or the intercept. Um, so yeah, so when you're doing it practically, you will have to do it using gradient descent rather than going through all the infinite values of the slope. So you don't actually calculate the values of all the possible rotations of that line. You actually just start optimizing over the least square curve, right? I hope that makes sense. Um, so moving on. Uh, Now, once that you have got the values, like once you have the best fit line with you, after running gradient descent, what you want to do is you want to understand the goodness of that fit. So how well that particular line has fit to the data, right? So how well is it able to predict y based on whatever x or whatever feature you are providing. So for that, we use the statistic called R squared value. So, and it is essentially calculated uh, by using the sum of squared errors over the base model, which is essentially just your target variable, which you can see here. Just so what we do is we take the variance of the target variable over the mean. So this value is the mean of, and this is your y, and this is x. So y is your target variable, right? So what we are doing is we are just trying to calculate the variance over the target variable. So here you can see it's simply calculated by the value that you have for that particular data point minus mean square upon total number of values. So that gives you the variance over mean for the base model. And then you want to do that same thing for your best fit model. So once you run gradient descent, once you have that best fit line through the data, right? So now after doing it for just the target variables, now you want to do it for the actually fitted line. So that the same thing you will do for the best fit model. And once you do that, R square can be calculated by this formula. You can simply take the difference between the variance of your base model and your best fit model upon the variance of your base model. So what R square is telling you is that it is telling you the influence of that particular variable on your prediction. So for example, if R square is let's say R square is 0.6, it means that it means that the current variable that you are analyzing is contributing to 60% of the variance in the target variables value. So it essentially tells you the influence of a certain variable on your target. So that's why we calculate R square, right? And that is one thing. And then after this, so right now what we're trying to do is we are trying to see how good our model is, the best fit model that we found after running linear regression. Now we are trying to find different statistics for that model, some metrics through which we can measure the efficiency of the model. That's what we are doing. So R square is effectively, it allows us to do that how good or how good is the fit of that model, how much is a certain variable contributing to the final decision making, right? And similarly, we can also calculate the p-value, right? P-value is also a statistic which is very helpful in understanding how well the model, how well the data has been fit in the model. So this again, in order to calculate the p-value, you first have to calculate the f-score. F-score essentially can be given by this formula here, where you're again summing over the mean, the base model, like R square value, the same thing what we did there. But in this case, we also, now why do we calculate this? Because in case of R square, we are just getting the contribution of a certain feature on the final target variable. But this also allows us to understand how the model is performing over randomly sampled data. So using the F score, what we can do is we can eventually calculate the p-value, which tells us about the robustness of the model. And smaller the value of p that we calculate, the better is the fit of that particular model. So in this case, again, we are doing the same thing. We are calculating the sum of squared errors over the base model, difference with your best fit model that you learn from running the regression. Now this p is basically the number of parameters that you are using in your best fit model. So number of parameters in a simple linear regression is going to be 2, because the slope and the intercept. And this is again the number of parameters in your base model, which is again, you can assume it to be 1 or either 1 or 0 based on whether you're using the intercept, because slope is going to be 0 for sure. So it's just whether you're using the intercept or not. So based on that, this parameter could be either 0 or 1. This will be 2. Depending on a single variable, like a univariate analysis that we are trying to do right now, right? So using this, we can calculate the value of f for the whole data set, right? Now what we do is we randomly start sampling the data. So this is f value once you calculated, let's say it's called global f value for the complete data set. Now what you do is now you randomly sample the data, right? Once you sample the data, you again run linear regression, you get the best fit model, you again do this calculation and get F1, for example, for the first sample. Again, you get F2 for the second sample, F3 for the third, after doing the third sample, right? So you get different values of F. And let's say you are plotting these values in a histogram, for example. So if I get, I'm getting F as 1, then 2, then 3, then 4, 5, 6. So how many times am I getting, each time I sample, and I get 1, I put it under this bin. I get 2, I put it under this bin. And I create this histogram. Now, essentially, what we are trying to do is we are trying to find we are trying to find the maximum value that f can go. So, for example, uh, if you see here, the global value of f, we want to maximize this, and from the samples that we get, right? From the samples that we get, the values of f that we get for each sample, we try to find the maximum value, right? So, for example, let's say we got f, the global f, we got it as 4. And then for 3 random samples, we got a value higher than 4. Let's say 5, 6, 7. That's what we got f as. So the p-value is going to be, the p-value can then be calculated by the number of times you got value greater than or the f value greater than or equal to your global f. So 1, 2, 3, 4, 5 upon the total number of samples that you took, which is, I'm not going to sum this up now, but let's say 20, for example. So this gives you the p value, and that essentially tells you how good or bad the model has fit to your data. And smaller the p-value, better, which intuitively makes sense. So you're not, so random samples are not predicting higher values of f than your global value, which is what you want to do. So that this is one more statistic that will be very useful in evaluating your model along with R-square. Right? So this is how you can evaluate your trained model. Now moving on. So till now we did univariate analysis where we have a single value of x and we are predicting some value for y, right? Next, what if we have to do a multivariate analysis, right? Where we have we don't just have x to predict y, we have x1, x2, x3, and essentially we have to use all these to predict y. It really doesn't make any difference to the technique that we have followed, because essentially linear algebra allows us to treat each of these independently and run a regular gradient descent using partial derivatives over each of these variables, and you could optimize over n number of parameters. So that is not a problem. Like I showed you earlier, when I showed you the gradient descent over slope as well as the intercept, and I took partial derivatives with respect to the slope as well as the intercept. So similarly, you can do a multivariate analysis, like a multivariate regression, or it is also called multiple regression, using more than 2 parameters. But there's another catch to this, is that you can't really use R squared for evaluating your model when you have a higher number of parameters, because R squared tells you how much variance is there. Right? How much variance in the dependent variable is explained by the model. That's what R squared is telling you. But the problem is, if you increase the number of features in your model, the value of R squared will always keep on increasing. So sometimes, even if the feature is not really adding to the predictive capability of the model, your R square will still keep increasing as you keep on adding features. So you can't really use R squared for a multiple regression model. So what you want to do is you want to use adjusted R square. So adjusted R square, essentially what it does is it penalizes the model for unnecessary predictors. So basically it factors in the parameters, the number of parameters in the model as well as the sample size in order to do that. So adjusted R square only increases this adjusted R square, it will only increase if that particular parameter, whatever you're adding, is improving the actual model. Only then only then will it increase. And maybe I can just give you the how it works. So if you want to calculate the adjusted R square, it is 1 minus one minus the difference between your negative your total R square value, right? The previously calculated R square value, which is going to be very high, right? And then you essentially penalize this value with your model parameters. So these are your number of observations so in your data set, and this you divide by your observations minus the number of parameters in the data and minus one. So this essentially gives you the value for R square. Sorry, adjusted R square, and this will work in so in multiple regression. Usually, this metric is used for evaluating the model. So yeah, so this is what linear regression essentially is, and how you can fit a line to the data, how you can evaluate the best fit model, and what are the metrics that you can use, and then how do you expand it to go to multiple regression. So yeah, that's about linear regression. I'll take a quick pause here. If anyone has any questions regarding linear regression, feel free to ask, and then I will move on to logistic regression. Okay. All right. So I will take the silence as no questions there, and I will move forward, with logistic regression. And in logistic regression, what we are trying to do is the same thing as linear regression. Like linear regression, you're trying to fit a line, and using that line, you're trying to predict a value, right? Like what will be the value of that for that particular predictor? What will be the target variable value? In logistic regression, it's the same thing, but instead of predicting a value, you're predicting a class now. So essentially, you are doing for the purpose of simplicity. Let's say you're doing a binary analysis, right? So let's say if a certain transaction, if a certain financial transaction is fraudulent or non-fraudulent, right? So if you look at this plot, when I plot those data points on a graph, I can't really get much out of that data, right? Because it is either going to be 0 or 1. And if suppose I have just one variable, which let's say this variable is amount of the transaction, right? If I'm using amount to predict whether a transaction is fraudulent, or 0 means say non-fraud and 1 is fraud. So if I'm using this variable to predict if a transaction is fraudulent or non-fraudulent, I try to plot it on a graph, I won't really get much out of it, because as you can see, let's say as the amount is increasing, the number of fraudulent transactions increase, and as for smaller amounts there is lesser fraud. So there is no fraud. This is what we can see in this graph, but we can't really draw a line through this. We can't do much with this information, right? So essentially what in logistic regression, what we try to do is we try to fit a sigmoid function, or let's call it a swiggle, through this graph, through this plot. So essentially what I will be trying to do is the same thing. So you will see that it's very similar to linear regression, but in this case also we will try to fit a line, but in order to get some distribution over probability. So we are trying to fit a swiggle through the data. right? And then once this squiggle is fit, it will basically tell you the probability of a particular data point. So what this will do is it will bound the data between 0 and 1. So your y-axis will become your probability of that data, of that particular data point falling in one of the two categories, which is either non-fraud or fraud, right? And based on the curve that you fit over here, we can predict the probability of the data point falling either in fraudulent or non-fraudulent category. So if I project this particular data point on this curve, let's say it falls over here and say 0.4, right? So if this data point falls under 0 on this swiggle and it falls on 0.4, I can and 0.5 is my threshold for saying that, okay, above 0.5, if there is any data point which has a probability above 0.5, I will say that it is fraud. Below that, I will say it is non-fraud. So this data point will be classified as non-fraud because my curve that I fit to this data predicted that that it is my probability is zero of this point being a non-fraud of being a fraud is 0.4. So essentially, it is so essentially this point will be classified as a non-fraudulent data point. But I mean, as you can see, that is not the case because actually it is a fraudulent data point as it lies over here. So I will have to optimize. I'll have to further optimize my model for it to fit better to this data. So essentially, we are trying to fit a swirl or a sigmoid curve through our data. Now, to give a better intuition, we can't really directly fit a sigmoid curve to this data. So what we want to do is somehow we want to fit a line through the data so that each of these points can be represented on that line. And what we can do is we can use a logic function, which is this, right? In order to scale these data points from 0 to 1, we can scale them from minus infinity to infinity, right? As you can see in this particular case. So what happens is we scale these data points from negative infinity to positive infinity, and then we take the projections of these points on this line, right? So now this becomes a problem similar to what we saw earlier in linear regression. Now somehow we were able to start with a random line, right? And which has a random slope, just like linear regression. And we are able to project these points, all the data points on this line, right? Once you project these data points on the line, now we can do some kind of analysis with this data because now we have some gradient of values and not everything is not between 0 and 1, right? So that's what we do. From this point, we will again calculate the residuals between these points, right? We will project them on the candidate line that we have got, and that will give us some y-axis value. Now, obviously, x-axis is not of much use in this case because it's starting from infinity, and infinity minus whatever you're doing, you will get infinity. So these values are of not much use to us. What we want, what we are concerned with is the y-axis value. So these are also called as log odds, right? So these values will help us to to basically calculate some kind of a to calculate some kind of a metric, or to calculate some to quantify how good or bad this line is fitting through our data, right? So what we do is these values of log odd that we are getting, for each class we will we will multiply all the data points or the log odds of all the data points, right? So each data point will have some odd and in each category, and we will multiply them with each other, and we will finally reach a certain value which is called log likelihood. And that log likelihood will tell us how good or bad this line is fitting through our data that we essentially projected, that we basically scaled up our data to from minus infinity to infinity, and then we projected the data points on this line. And again, this line we started randomly. This is something that we just started off with any line, just like in case of linear regression, we saw that we started with a horizontal line and started tilting it. This is a very similar scenario where we start with a line of random slope. We project all our data points on that slope, and then we calculate. So simple process, right? We take a random line, we project all our data points. We assume that this class is at infinity, this class is at negative infinity. Project all your data points on that line. Then look at the y-axis for each data point. You'll get the log odds. Multiply all the log odds for each of these categories, and you will get the log likelihood, right? And so one, for each class you will get the log likelihood. So if it's a binary classification, you will get log likelihood for one class, and then once you can do 1 minus the likelihood of the current class to get for the other class. Now what you want to do essentially is you want to maximize the value of this log likelihood for your line to be the optimal fit to the data, right? So once you calculate the likelihood, log likelihood for one line. So let's say we did all the multiplications over here, and we got the likelihood, right? For overall likelihood, we multiply all the individual likelihoods together. That's what we did, right? We got the overall likelihood for this line that we started with randomly. Now, once we have this overall likelihood, we will follow the same technique that we followed in linear regression. We will tilt the line a little bit, and we will do the same process again, right? We'll rotate the line, do the same process again, compute likelihood again, and again, so we get the final likelihood, right? We get the log likelihood for line number 2. For line 2, we do the same thing. For line 3, we do the same thing. And we keep on tilting till we get all the possible log likelihoods. And then simply you take the maximum value from that. So whichever line gives you the maximum of your log likelihood is the value, is the line that is fitting your data the best. And then you can simply take all those data points on that line, run them through a sigmoid function, and you are back with that. Essentially, you are back with the swiggle, and you will get a probability distribution over all the data points that were fit to that line. So this essentially is called maximum likelihood estimation, in which you are trying to maximize your log likelihood by trying multiple values, right? By trying multiple values of the slope. But again, this is also not practical, as we saw in linear regression. because of the same issue that that you can't really try infinite number of lines, like infinite number of slopes, and you can't keep on tilting the line, right? So in this case also, you can use gradient descent. So in this particular case, you want to maximize over you want to maximize. So you could either run a gradient ascent, or what in practice what we do is we run a gradient descent algorithm on negative log likelihood. So essentially you are maximizing log likelihood by minimizing over negative log likelihood, right? And that's so you run your descent on negative log likelihood. I can show. Let me show this mathematically once so that uh, it makes a little more sense. Uh, let's say, so for example, you have your data like this, right? You're fitting a sigmoid through your data. Your data points are going to be somewhat like this, as we saw earlier. Now, when you're trying to predict the value of your target variable value, right? Essentially, you're running it through a sigmoid function. So sigmoid, as we know, is just 1 by 1 plus e raised to minus x. So this is the value of your sigmoid function. This x, if you substitute here, you will get your target variable. Now, when you are running a gradient descent for a classification problem, you're trying to maximize the log likelihood, or you're trying to minimize the negative log likelihood. You essentially, your cost function is called a binary cross entropy function, which looks something. So if you have theta is the parameter that you're trying to optimize on, essentially your binary cross entropy looks something like this, where it's yi, which is the actual value of the target variable, into log of y hat. Let's say, y hat is this value, that predicted value, actual value into predicted value, plus 1 minus actual value into 1 minus the predicted value. So this essentially becomes your cost function over which you are trying to optimize. Of course, this goes from 1 to n. N is your total number of data points. Now, when you differentiate this based on your parameter theta, you will get. I mean, this now, if I try to sit and differentiate with respect to x, let's see, I will, essentially, I can see this. I mean, essentially, you will get some value of x. So essentially, what you're doing is you have your cost function. You're taking partial different, you're doing a partial differentiation with respect to whatever parameter that you have, and then so once you get this gradient, once you calculate this gradient, so this will be an x, right? And once you get this value, you can update your your parameters based on the old value of parameter, similar to the normal gradient descent what we learn, right? You have a learning rate, the value of gradient, multiply them, reduce them from your previous value of your parameters, and you get the new parameter, and you keep on running this, right? And I mean, if you really want to take partial derivative, so because this is a little tricky here, because y hat is your sigmoid. Now, if you want to do it manually, like sigmoid function is this, right? Can be given as 1 upon 1 plus e e raised to your whatever variable, let's say z, right? Now derivative of sigmoid is sigmoid of that variable into 1 minus your sigmoid. So you could, so basically this needs to be worked out in this particular equation, and you don't, and then eventually you will reach the gradient value, but you don't really need to worry about that. And I mean, you can solve for this and then eventually come to this, and that will be your gradient. But when you're implementing it, this is all taken care of in the backend by whatever package that you're using, may it be scikit-learn, may it be TensorFlow, PyTorch, or whatever. So this is essentially how gradient descent would run on a logistic regression problem, right? Um, okay, so that gives us some detail about that tells us how we essentially reach the best fitting line in logistic regression, and then using that line we pass that data through the sigmoid function, and we get the optimal distribution, the optimal probability distribution over our data set, and this is called maximum likelihood estimation, right? um, Next is, again, how do we evaluate how good or bad um, a model is? Like, once we have fit the model to the data, we want to understand how well the model has been fit to this data. In order to do that, we have something called as a statistic called as z value, right? Now, z value is essentially, it is a statistic that tells you how many standard deviations away from zero a certain parameter is. Further away, better for us. Means it is showing more variance, and it is better, that particular parameter is good for the model, right? So uh, basically, it is, so z value is essentially given by the estimated parameter. Like, you can calculate z value by estimate, like the value of the estimated parameter divided by, now this I haven't added this slide, but let's just say, let me just give you the formula here. Upon the standard error, right? So what z value is telling you is, for example, if z value is 2, it means that the estimated parameter is at least 2 standard deviations from 0. Hence, so if it is that much far away from 0, it is considered as a, usually plus or minus 2 for z value is considered to be a statistically significant parameter. And that parameter is that parameter is considered then a good estimator of your model. So that's where we are using z value. Now, the estimated parameter value you can always calculate. Standard error calculation is a bit engage, like it needs some further understanding of how linear algebra works, essentially, because so standard error, when we calculate it in for practical purposes, it is usually calculated by using the diagonal values. So we have a, once we calculate a Hessian of log likelihoods, so second order derivatives of the log likelihoods that we calculated early on the using the best fit lines, right? We take the inverse of this matrix, and the diagonal values of this the number of columns that these matrix have is equal to the number of parameters that you're using. since we are using multivariate analysis, since we are doing univariate analysis in this case, we don't really have a matrix. We just have a vector in our case. But if as the number of variables, as the number of features in your data set increase that you're using to predict, this kind of scales up, this matrix kind of scales up, and then you have to calculate the second order derivative, which is also called as Hessian of that matrix. Take the inverse, and the diagonal entries essentially are how you reach the standard error. So yeah, this is it is not important to get into this right now because that will complicate things further. So let's ignore that. But yeah, so z value is a statistic essentially that, and again, this is a part of standard scikit-learn packages or stats model package where you can directly just input your fitted model to and call that class of z value, and it will give you that it will calculate that metric for your trained model. So you don't have to really worry about implementing this while you are performing any kind of this model analysis. And finally, I also wanted to just give you a brief about how categorical data is treated. So now, as of now, what we saw is the x-axis was always continuous data where we saw as the amount is increasing. So amount is continuous data again, right? As amount is increasing, the probability of fraud is increasing and all that. But now what is the data is categorical, right? For example, in this case, you can see that there we have two distinct categories within our data set. And what we are trying to do is how do we use this in our regression model. So whenever we have categorical distribution, categorical parameters in our data set, what we can do is we can simply just calculate the logit functions. Like we can essentially calculate, we can run logistic regression through each of these categories separately, right? So what you can do is you can fit a swiggle to this category as well as you can fit a swiggle to the along this category. So along this category. And then once you get both, once you calculate the log out of both, you can essentially just find your target variable. So you can calculate your target by taking one of these as the baseline. So let's say I took my class 1 as the baseline, calculated log odds, plus I take the relative variance. So log odds of C2, class 2 with respect to C1, and then the log of that. And this, so as you can see here, even if I take my baseline class as C2, my final calculation will still be this is actually equal to this. So irrespective of what your baseline class is, you just take one of the classes as baseline and you calculate the estimation, the log likelihood estimation based on the rest of the relative variances of the rest of the classes. And that's essentially how you can use categorical data to train your logistic regression model. And yeah, so and that's pretty much it for logistic regression as well. So here also we learned how we can fit a line through your, first of all, you have categorical data. You project your data on a line. What we learned is we essentially project our categorical data on a line with a random slope. Then we calculate the log likelihood of the log odds. So basically what we did was we projected just give a refresher here. As you see, we projected all the data points on a certain line. We got the log odds. We calculate the total log likelihood based on all the loggers for that line, and that log likelihood we got for one line. Similarly, we want to do it for all the possible lines. For that, we run gradient descent over the binary over our cost function, which is in this case a binary cross entropy loss, which we did here. This Yeah. So this is our binary cross entropy loss function. We took partial derivatives, we updated parameters, and we eventually uh, iterated over this to find the optimal parameters. That's how you get the best fitting line. You take the best fitting line, you run it through, you basically pass that line through a sigmoid function, and you again are back to a swiggle, and that is your optimal curve that is able to separate your data in the best possible way. And that's how you run a logistic regression. Yeah, and then we learned z value, which is a statistic that gives you an estimate of how good or bad your model is fit to the data. Yes, so yeah, with this, I would like to stop at this point. And so today we covered linear and logistic regression, and tomorrow we can move forward with other supervised machine learning algorithms, which are a little more advanced than this. Any questions?
Hello.
Yeah.
Am I audible?
Yes.
It was a wonderful session, but I do having one curiosity to know that I do having the I do having the Excel sheet of the data. Okay, so how come one can decide whether it is fitted for the linear regression, multiple, or a logistic? The methods we learn, that is, and the testing, it's good, but on our raw data, how one can decide it, which regression should be a good one?
Okay, yeah. So that depends on the problem that you're trying to solve, right? So, for example, you have an Excel sheet in which you have a bunch of data points, right? For example, you let's say you have information about,
I do having the business process data.
Okay, and yeah, let's say business process data. Okay, so let's say you have some variable x1, x2, x3, and then using and this is all in an Excel sheet, right? So these are all your columns, x4, these are all your column names, and using all this, right, using all these variables, what you're trying to do is you're trying to predict y, right? Y is another column in your data, right? You have your business data in which you have a bunch of different data points. Using those data points, you're trying to predict a value. So in your business, can you give me an example of what your business data looks like and what you're trying to predict in that data?
It's like I buy something as a commodity material and estimate that is what kind of quality I can achieve from those things without processing on those.
Okay, so
then I process on it, and then I do having the another things are coming, which the person one who can estimate from the raw, person two who can estimate from the processing, and the third one is after entire finish, you having the certain third things are coming. So under this, there are certain losses also, but I just want to predict.
So yes, what is your final target? Like what is
final target is if I am procurement from the X vendor, okay, and Y vendor, where I am getting my predictions are perfectly fit.
where, okay, so which vendor should you choose? That's your
There are the n number of vendors.
n
Okay.
vendors.
From which vendors
Okay. Yeah.
and
Yeah. Got
persons
it.
are estimated where it is fitting best.
Okay. Got it. So yeah. So this again. So see, you have n vendors and you are trying to find which vendor is the best fit. Correct. And
Yes.
that is a again. So what is a vendor? Vendor is a category, right? So you n vendors are n categories that you have. So this is not a you're trying to predict what category does a certain data point or a certain row of your data set fall into. So this becomes a logistic regression or it becomes a classification problem. So in this case, for a classification problem, as we learned, logistic regression would be an ideal way. Like, of course, it might not be the best for your data set because there are many other classification algorithms that you could try. But as a baseline, you could start with logistic regression, and that would help you to predict what category of vendor that particular data point falls into, and then you could use a bunch of other algorithms as well. But yeah, between linear and logistic regression, this particular problem that you are speaking is a classification problem. So you are supposed to be using something like logistic regression, some classifier for this rather than a regressor. Does that make sense?
Okay, okay. And one more thing, if I do having the time series data of my commodities, okay, that is
Okay.
the price value, then can I use the regression and which regression for the prediction of price?
Yes, yes. For that purposes, so since that is a continuous variable, you could be using regression for that. But since it is time series, right? So time series data is essentially there are other techniques as well to model time series data, um, which are specifically developed for time series analysis. So you could start with linear regression, but then there are things like you want to look at ARIMA, ARIMA, SARIMAX. So these are all these algorithms. They are specifically built for looking at seasonalities within time series data sets. So and of course you have some advanced deep learning models as well, like LSTMs, GRUs, which you might want to take a look at if you are actually working on some like you're trying to find some optimal way to to model this problem that you are facing or whatever you're trying to do. So maybe linear regression is a start, but you for time series data you really want to go for some better specific models which can be used for time series analysis. Does that answer your question? But yeah, you're right. You can use linear. You can start with linear regression. All right. Any other questions?
Hey, hi, Prashant. Owen here. One question.
Mhm.
In the linear regression, we can use the fit function for finding out the coefficient and intercept value. So
Correct.
the same things we can achieve in a logistic also, or there is a another way to find out the to uh, by using another function.
Oh, so you were talking about implementing the code, right? When you're implementing the code in whatever package, maybe you're using scikit-learn, you're doing a model.fit, and then after running the fit, you get your intercept and
Mm-hmm.
the set value, right? Yeah.
Yes.
So yeah, same thing will work for logistic as well.
Okay.
Any other questions?
No.
Yeah, okay. All right. So I guess we can stop here. Baba sir, are you there?
Yes, yes.
So sir, we can stop here and we'll continue tomorrow.
Yes, if no more questions, stop. Thank you very much. Thank you.
All right, thank you.
Thank you.
Thank you all for attending today's session. I would request all of you to please give your valuable sessions feedback. The feedback link is shared in the chat box.